This lesson is for section 1.3 on techniques for finding limits. We have two objectives for today. Our first objective is to go over some theorems that will allow us to simplify problems that involve limits. Our second objective is to use the sandwich theorem, which is also known as the squeeze theorem, to find a limit. So I've got some good news for you. This lesson is all about how we can exploit somebody else's hard work to make the process of finding limits pretty easy for us. So it would be an insane amount of work for us, very excruciating, to have to verify every limit by means of our precise definition of a limit. So rather than continuing to use that delta epsilon definition to verify limits, we're now going to rely on some theorems that have already been proven that will simplify our task for finding limits. So let's get started with our first two theorems, and these are theorems that we're going to rely on for the rest of those theorems written to the side. Now, since these theorems here, these two are very quick ones, I'm going to take the time to prove them, but afterwards we're just going to summarize the rest of those properties that you see for limits on the right. Alright, so let's start with our first theorem here. We want to prove that the limit as x approaches a of a constant function c is equal to c. So in other words, we want to show that the limit of a constant is, instead of it saying a constant, it should say the constant. So just to be more clear here, our function f of x is c. This is our function. It's just a constant function, which means if we were to graph this, this would be a horizontal line. Okay, so here's f of x. Alright, so what we want to show in our proof is that for any epsilon that we choose, we're always going to be able to find a delta, okay, such that if the distance between x and a is less than delta, then the distance between our function and our limit should be less than epsilon. Alright, so let's remember that when we're working with proofs, we actually work our way backwards. So we'll start with that inequality here. So we have the distance between our function and our limit is less than epsilon, and we'll just make some substitutions. So our function here is c, that's our constant, and our limit also happens to be c. So we're left with this very trivial inequality here. 0 is less than epsilon. Remember, we are solving for delta here when we work our way backwards. So really this is telling you that if delta is equal to epsilon, then delta can be any number. You can choose any number that's greater than 0. So no matter what value of delta we choose, our function will always lie within a distance of epsilon away from c. So if we draw that in, you can see it, I think, a little bit better if we actually make sense of what this is saying. So here we've got, let's say that this is c plus epsilon, and here is c minus epsilon. Now, whatever delta we choose, so here's a, okay, whatever delta we choose, we can make this interval as large or as small as we want. Let's say that delta is this wide here. So we've got, here is a minus delta, here's a plus delta. Okay. Now, no matter what, you're still always going to map back inside this red zone here, which I just colored in orange, but you'll always go back to that red zone, no matter how large or how small you make that interval. So delta can be any number at all, because again, if I make that a wider interval, if I make this a larger delta, then I still get back inside that red zone here no matter what. Alright, so let me erase real quick, and we're actually going to do the proof part. So we just found our delta. That helps us to write the actual proof. Remember, delta can be anything. Alright, so if we let the distance between x and a be less than any delta that we choose, our function will always lie within a distance of epsilon away from our limit. So then f of x, which is c, minus our limit c, is going to equal 0, but that's still going to be less than epsilon. So no matter what delta we choose, our function will always lie within a distance of epsilon from our limit. And that is the proof for the first theorem. Now, in our second theorem, we want to verify that the limit as x approaches a of a linear function x is equal to a. Now let's make this proof a little bit easier by defining f of x to equal x. Okay, so we want to prove that the limit as x approaches a of f of x is equal to a. So again, we start with if the distance between, x and a is less than delta, geez, that's messy, then the distance between our function and our limit is less than epsilon. So again, let's start with this inequality here. So we have the distance between our function and our limit is less than epsilon. Now, we're trying to solve for a delta so that we have it in terms of epsilon. And if we make some substitutions here, f of x is equal to x, and our limit is a. So we have the distance between x minus a is less than epsilon, which means our delta is equal to epsilon. All right, so the point of this scratch work here is normally to find a delta in terms of epsilon. Usually it's something like delta is equal to epsilon over 3. Well, in this case, delta is equal to epsilon. So what that's really stating is that you can choose any delta that you like. So if the distance between x and a is less than any delta that you choose, then your function, the distance between your function and your limit will always be less than epsilon. Now, if we make some substitutions, we can see that this is true because we end up with x minus a, right? F of x was x, our limit was a. We have x minus a is less than epsilon. We know this has to be true because delta and epsilon are equal to one another. So we have proven now that the limit as x approaches a of x is equal to a. All right, so those two theorems that we just proved are actually used extensively in the proofs for these properties, these theorems that are listed for limits as well. Now, we're not actually going to prove every single one of these theorems. In fact, I'm not going to read off every single one of them to you either because I think they're pretty intuitive to understand. So I just want you to make sure you do skim over them. But I want to kind of point out a couple different things here. So rule number 1, this first theorem here, states that if you find the limit of a sum, so here we're adding f of x and g of x, two different functions here, we can actually find the limit here by taking the limit of each function and then adding them together. So the limit of a sum is the sum of its limits. Now, like I said, I'm not going to read off every single one of them because I think that's pretty intuitive and so are the rest of these. But I do want to make note of the way that they've introduced these theorems to you. So these properties came straight from your textbook, right? And now if you pay attention to this order here, how we went from 1 to 5, you might find it kind of odd that they put the limit of a difference all the way at the end instead of right after the limit of a sum, because normally we think, okay, adding and subtracting and then multiplying and dividing. But the reason why they did that I find is pretty interesting. They chose to put this one last instead of after the sum because it's much easier to prove the limit of a difference is the difference of the limits after you have other theorems available to you. So in this case, you would want to combine this first theorem along with theorem 4, right? Because theorem 4 takes a constant multiplied by some function. So in that case, we could write f of x minus g of x as f of x plus -1 times g of x. Okay, so that's just showing you that you can use theorems 1 and 4 now to prove theorem 5. All right, so thankfully we don't actually have to use the delta epsilon definition to prove each and every single one of these theorems. But the reason why we go over these properties of limits is the fact that now these theorems are available to you. Okay, we didn't prove them, but they have been proven. So now we can actually use them. Back in our first section when we found limits of functions, we were doing things intuitively. We were looking at graphs, we were looking at tables, and then we realized that, hey, if we just algebraically, manipulate this function, or if we evaluate the function, we'll find a limit. Well, now we have definite reasons for why those steps worked. Okay, so here we now have theorems that kind of back up all of those things that we intuitively thought would work. Well, now we have a reason why they do work. They've been proven to work, so now we can use these properties as we continue to algebraically prove that limits exist. Okay, now let's apply those properties that we just talked about to the graph of f of x and g of x and answer a few questions on finding limits. So first up, we're asked to find the limit as x approaches -2 of a sum. Now within that sum we have a constant multiplied by one of those functions. So if we break this down using our properties, we can rewrite this as the limit as x approaches -2 of f of x plus 5 times the limit as x approaches -2 of g of x. Now it's much easier to use our graph here to answer this question. So if f is the red graph here, or I guess the purplish kind of graph here, we want to find the limit as x approaches -2. So as x approaches here -2, it looks like the limit here is 1. So we have 1 plus 5 times the limit of g. In this case, that limit of g here would be -1. So we've got 1 minus 5, which is going to be negative 4. So the limit of f of x plus 5 times g of x as x approaches negative 2 is negative 4. In B, we're finding the limit of a product. So if we want to rewrite this using our rules, we can write that as a product of limits. So let's find the limit as x approaches 1 from the right of f of x, and then we'll multiply that by the limit as x approaches 1 from the right of g of x. Okay, so this is a product of limits. Okay, so let's evaluate. The limit as x approaches 1 from the right of f of x looks to be 2. Okay, and the limit as x approaches 1 from the right of g of x looks to be negative 1. So we multiply here, and the limit of that product is negative 2. Okay, I'd like you guys to try C on your own and check that one with the key. Let's work on D. D asks, does f of negative 2 equal the limit as x approaches negative 2 of f of x? So let's first evaluate each of those. So f of negative 2 is equal to 2. Okay, the limit though as x approaches negative 2, that's actually 1. So no, they are not equal to one another. So this is again just highlighting the point that it doesn't actually matter what happens as x approaches a, it doesn't matter what happens when x equals a. All that you care about is what happens as x approaches some a value. Okay, we continue now with some additional properties of limits. Now, we're not going to prove each and every single one of these theorems because, again, it would take a rigorous proof to show using the delta epsilon definition that these theorems do hold. But you can really gain an appreciation for them if you try to use the delta epsilon definition for any of these problems here. You can see how powerful these theorems are. Having these theorems available to us makes evaluating and finding these limits very easy. All right, so I just want to mention one more time that the reason why we are introducing you to these theorems is not for you to memorize them, so please don't do that. That would be very overwhelming. You all have already been using these theorems just intuitively. Way back in the first section on limits, when we were evaluating, and finding limits of functions, we said the first thing you want to do is try to plug in a value, and that's exactly what you would do here as well. You would plug in 3 into that function here and just evaluate at x equals 3. So we end up with 6 minus 3 to the 4th power, so we get 81. So the limit as x approaches 3 of this function here is 81. Well, technically, you're using theorem 2, but you don't need to know it or have it memorized in order to use it. But basically the reason why we show them to you is to show you, hey, the steps that you're taking are verified, they have been proven, so now go ahead and do those steps. So basically we avoid having to do any more delta epsilon proofs to show or verify limits. Okay, now for 2 and 3, I'm just going to pause the video and work it out so that we can talk about them, and then 4, we'll do some algebraic manipulations. Alright, so I just put some of these on here just because evaluating these limits is a little bit trickier. Here we just straight away plug in 3 and we find a real number. So we have the cube root of 24 after we simplify, and then that reduces to 2 times the cube root of 3. So you can see the intermediate steps that I've taken in case you're not following that. Now for number 3, once I plug in 8 into this function here, I end up with 2 squared plus 3 times 2 root 2 over 2. So just factoring out a common factor of 2, I end up with a limit of 2 plus 3 root 2. Now, in number 4, when I try to plug in x equals 0 into this function here, I end up with the square root of 4 minus 2 over 0. So I end up with 2 minus 2, so 0 over 0. This is called an indeterminate form. Okay, because you can't determine what's happening, around the value of 0, because you get 0 divided by 0, it's undefined. So you've got an indeterminate form here, which means we have to do a little bit more work. Now, that work that we're going to do here, I'm going to pause the video, but we're going to multiply by the conjugate to try to get rid of that radical. Okay, now by multiplying by that conjugate in the denominator, I've created a difference of squares. So if I were to FOIL this all out, you would end up with a product that looks like this: x squared plus 4 minus 4. So that's a difference of squares here. So I just took the first term and I squared it, and I took the second term, I squared that, and I put a minus sign in between. Now in the denominator, I still have x times the square root of x squared plus 4 plus 2. So notice it didn't get rid of the radical yet, but that's okay here because in the numerator, that reduces just to x squared. So I have x squared over x times the square root of x squared plus 4 plus 2. Now if I factor that out, that x out, I have x over square root of x squared plus 4 plus 2. Now again, I didn't get rid of the radical, but I'm not don't really care about that because all I'm interested in is evaluating this function at x equals 0. If I now plug in x equals 0, I will end up with 0 divided by the square root of 4 plus 2. So I have a value. This is a real number. This is defined. This is 0. Okay, so the limit as x approaches 0 of this original function, let me erase here, it is equal to 0. So even though when we plugged in 0 into that original function here, we ended up with the indeterminate form 0 divided by 0, that indicates, right, that the function is undefined. So in other words, x equals 0 is not in the domain of your function here because you get an undefined value. But even though it's undefined at x equals 0, the limit as x approaches 0 is 0. Okay, that means everywhere around that value, it's approaching 0 from the left and from the right. All right, let's move on now to the sandwich theorem, the last part of our lesson. All right, next up we have the sandwich theorem, which is also known as the squeeze theorem in certain textbooks. Okay, so the sandwich theorem states that if you had three different functions here, and they follow this relationship here, so the values of f of x are less than or equal to h of x, which are also less than or equal to g of x for every x in an open interval containing a except possibly at a. Again, remember, you don't really care what happens usually at the value x equals a. But if you know that the limit as x approaches a of f of x is L, and you know that the limit of g of x is also L, so these two limits are the same, then that means the limit of the function in the middle, it's sandwiched between them, that will also equal L. Now, let me just visually explain what's going on here. I know I have a picture here, but you're seeing all of it all at once. So I want to visually kind of explain this first, and then we'll work on the problem. So we have some function g of x. So let's draw this in. And we have, for some a value on the x-axis, we note that the limit as x approaches a of g of x, that's equal to L. So off to the side here on the on the y-axis, I will write L here. Now, we don't care if g of x is defined at a to be L. We just note that it approaches the value of L as x approaches a. Now, let's suppose then that we have another function. Let's call it f of x, okay, where this function, the y outputs of f of x are always less than or equal to g of x. So you can kind of see it visually. These are always below the function g of x. Less than or equal to means below, or right here, as you can see, it looks like at x equals a, they are intersecting here. So it looks like they're intersecting there, but as x approaches a, the limit of f of x as x approaches a is also equal to L. So right now, we have these limits all equaling the same value. So now what the squeeze theorem does is it introduces now a third function. So it says that if you have a third function here, and we'll call this one h of x, and h of x is sandwiched between g of x and f of x. In other words, for the values of h of x, they're greater than or equal to f of x, but they are less than or equal to g of x. If that's true, then we know that the limit as x approaches a of h of x must also equal L. So if these conditions here are true, okay, then the limit as x approaches a of h of x must also equal L. All right, let's try to find the limit as x approaches 0 of x squared times the cosine of 1 over x. Now right away, we're going to just try to input 0 into that function. Now when we do that, we end up with 0 times the cosine of 1 over 0. So here we see that we get an undefined value here. So we can't really tell what's happening as x approaches 0. So in this case, we have to do something different. Now, let's look at this function, the cosine of 1 over x. I know that the cosine of 1 over x will always be contained between -1 and 1. So if you're not sure why I was able to set up this inequality, think about how you graph a cosine function. Remember, that cosine function will always oscillate between values of -1 and 1. So these outputs for your cosine function, no matter what you plug in, will always be between -1 and 1. Now this inequality allows me to manipulate it in such a case that I can create that function here by multiplying by x squared. So if I multiply by x squared in the middle here, I have to make sure that I multiply by x squared throughout, right? So I created an equivalent inequality. So I'll have negative x squared is less than or equal to x squared times the cosine of 1 over x, which is less than or equal to x squared. So what I've done is I've just created a situation where I have f of x, some function, which is less than or equal to h of x, which is less than or equal to another function, g of x. So I've just sandwiched this function here, the one that I'm trying to evaluate the limit of. I've sandwiched it between two other functions that I do know how to evaluate when x approaches 0. So in this case, the limit as x approaches 0 of f of x, which I'll replace as x squared, negative x squared here. Okay, that value is 0, because if you were to graph this too, you can see, okay, the limit is 0 here. Now for the limit of g of x as x approaches 0, this will also equal 0. Okay, now that function x squared times the cosine of 1 over x, I might not know what it looks like, but I do know that it's trapped between g of x and f of x. Okay, so that means the limit of x squared times the cosine of 1 over x as x approaches 0, this must equal 0. Again, because according to our sandwich theorem, h of x here is sandwiched between f of x and g of x, which means that if the limits of f of x and g of x here are equal, and they're both equal to 0, then the limit of h of x must also equal 0. Alright, so this problem can be tough if you don't remember how to use this original trick here. So whenever you have a sine or cosine function, you will be able to set the values between -1 and 1, which will then allow you to manipulate that inequality to create an inequality where you have your original function here set between two other functions. So you'll have to probably come up with f of x and g of x on your own, or the book might give you a little bit of a hint, but that might be the toughest type of problem that you're going to see from section 1.3. Alright, that is the end of the lesson. So ask good questions and get ready to work tomorrow. Nice job. See you tomorrow.